All right, good morning everyone, and welcome to the next Blue Waters webinar. My name is Maxim Belkin. I'm an education and training coordinator in the Blue Waters project at the National Center for Supercomputing Applications. Today we have a special webinar. This webinar is part of the our scientific workflows webinar series. It is titled High Performance Workflows with SWIFTIT. It will be presented by Justin Wozniak. Justin is lead research scientist for the SWIFTIT project. He works in the mathematics and computer division at Argonne National Laboratory. He also participates in the exascale computing project. So the webinar promises to be very interesting. With that, Justin.
Yes, hi, thank you, and thanks for the introduction, and thanks for joining. Today I'm going to talk about SWIFTIT, which is a workflow system for high-performance computing. I'll talk a little bit about what that means. And so I'm going to start with some applications and kind of go into then how the language works a little bit. So I'll probably do slides for about the first half hour, and then I'll run Swift on a local machine and hopefully on Blue Waters as well for the second half hour. So just to get started, I'll give just kind of two quick examples of large-scale workflows. So one is cancer ensembles. Let's say you have a agent-based model of a cancer model, and you want to run it millions of times. And let's say this model is relatively small. It's a small C++ program, and we want to run it say 6 million times to study the parameter space and model and figure out how to model the right parameters for this tumor. So we built a system with Swift for these kinds of optimizations and parameter explorations called EMEWS, and we were able to run the existing Python optimizers and R optimizers inside of Swift and distribute work across the blue gene queue at tens of thousands of cores, thousands of simulations per second. Even though each simulation runs for several seconds, the aggregate concurrency allows us to run many simulations per second in aggregate, and then we're able to then converge on a solution. I'll talk a little bit more about this framework later, but that's just one motivating application. Another is experiments where you have, let's say, the APS, which is an X-ray source here at Argonne, and you have data streaming in to the supercomputing system from the APS. You have hundreds of files, terabytes per week of data coming in, and you need to do different kinds of coordinate transformations and other kinds of analysis on these essentially image files that are coming in. It was relatively easy to write a Swift script to break up the easily parallelizable aspects of this and then do this kind of distributed image processing, which was actually a MAPREDUCE-like pattern, as you can see in the diagram. But basically, it was very easy to express with Swift and then again run at scale. So those are just two examples. So now I'm going to talk a little bit about how the SWIFTIT system works. And so starting with the goals, what are the goals? The goals of Swift are to make it easy to run large batteries of either external programs or library executions. So Swift is a hierarchical programming model. It is we think of it as capable of doing pretty much everything, but it's really designed to run hierarchically, where you're calling down into existing codes, simulations, analysis codes, typically often through the shell, but we can also call into libraries directly, and I'll show an example of that during the demo. And then also Python and R and other kinds of things like that efficiently. So we wanted to provide a rich programming language, so it's a very natural programming language. It looks a lot like C or Java. And again, it's fully generic, but it has a lot of workflow flavors. So it's got a lot of things that make it seem kind of like a workflow system. It's based on implicit concurrency, so everything is kind of declarative, and the system decides what can run at the same time. and it does it. But we do this with relatively conventional programming constructs. So you'll see a lot of traditional looking loops, conditionals, function calls, things like this in the language. But Swift is able to analyze these programs and then run them as concurrently as possible. Again, we enable complex tasks in other languages, so we have features to bundle in at configure time, the Python interpreter, the R interpreter, Julia, Java, all kinds of interpreters, so you can actually execute code inside of the Swift address space, actually, but inside of these other interpreters. And that makes for some very interesting mixed language programming capabilities. And then also MPI tasks. So Swift is very based in the MPI ecosystem. Swift is itself an MPI program, SWIFT is, and it's also capable of then calling into MPI tasks through a library interface. So if you have an MPI library, you can easily call that through Swift. Let's say you have your simulation code. Some simulations are already expressed that way, like LAMMPS. They're able to be called as libraries. And also you can also call MPI executables relatively easily from Swift. Then we have some new features for that too. And then other powerful features, data types, resource management, priorities, a lot of other things that you'd like to do when you're running scalable workflows. Oh, by the way, and feel free to use the Slack channel to ask a question at any time and stop, and I think the moderator will coordinate that. So the programming language looks a little bit like this. Here's an example. This is a function called myproc. It has 2 arguments and 1 return value. And then it's going to call into 2 other functions. It's not specified what F and G are, but they could be anything. They could be other Swift code. They could be calls into shell commands. They could be calls into some Python code. Who knows? But the point is that when Swift enters this function, all 3 of the lines of this body of this function are eligible to run at the same time, limited only by data dependency. So in this case, assuming I and J are both available, which they probably are, then F and G will both run at the same time. And Swift will find workers for them to run on and run them. In practice, what this means is that Swift, which is running as a big MPI program across a machine like Blue Waters, would then be able to send a message to a worker and launch F and G, regardless of what its implementation is. So this kind of automatic parallelism works throughout the Swift program, and it goes through the call graph of the program pretty deeply actually as it runs. So it's totally automatic parallelism. You don't have to specify, that I want F and G to run at the same time. They will run at the same time, and the synchronization for that final statement, the X plus Y, that's automatic too. So X and that's essentially X and Y are essentially futures, and you don't have to express them as futures or anything. It's just that everything is a future in Swift. And so then X and Y will be notified when their values are available, and then that statement will run, and then R will return some value, and then anything downstream that's depending on R will then be eligible to run. So based on those essential concepts, we have quite a bit of other syntax. So we have typical data types, integers, floats, strings. We have a file data type, so that means that you can do data flow and data dependencies on files. Of course, files are mapped to real files, so this file variable here, image, is then mapped to the file name snapshot.jpg, for example. And then you can do data flow on files, kind of like what you would do with a MAKEFILE, where you have data flow on files, essentially. So we have a nice syntax for accessing the shell. They're called app functions, so you can just with that app keyword, you can define a function, and that essentially connects a Swift type signature to a command line. So in that case, you can see that, we have an app called my app, and it's going to consume a file and an integer, and it's going to produce another file, and it's going to run with the command line shown, where it's, something called my sim. It's going to take an S argument, and then Swift is able to then essentially paste those values onto the command line to run. We have data types, structures. You can type def things. You can make arrays, structured types. That last definition there, B, is kind of complicated. That's essentially a MAPREDUCE bucket. It's a list of MAPREDUCE buckets. So it's an array of bags, and a bag in Swift is essentially an appendable array, and then each entry in that is a blob. So that's and a blob is a binary string. So that allows you to essentially take, kind of like a MAPREDUCE, build essentially a MAPREDUCE application around that, where you're inserting into all of those buckets, which in Swift are called blobs. And then in terms of control, we have conditionals that look like conditionals in another language. If we have for each loops, we have for loops that have slightly different syntax. Again, those run in parallel because it's based on the data availability. So if all of the entries in A are available, all of those convert tasks will run at the same time. And then also, DataFlow actually looks inside of the structure of different kinds of expressions, like this this case where we're going to merge the results of two analyze tasks, and those analyze tasks will again also run concurrently if possible. So a little bit about how we got here from Swift K and Swift T. So Swift K has been, we have, the Swift language has been around for a while. It's at least going back to 2007. That was a system built for grid workflows, and it was, and it's still supported and maintained for grid and cloud-like applications. But we wanted to see if we could extend this model, this programming language, to exascale. And what we realized was that we needed to emit a lot of tasks, right? Because on an exascale machine, we were going to have quite a bit more concurrency, and we were interested in supporting tasks that are much smaller. So we needed to be able to spit out tasks from the Swift program very quickly. So we completely rebuilt Swift from scratch. We kind of renamed the old one Swift K because it ran on the Karajan runtime, so K for Karajan. And then we have a new runtime called Turbine, and that is a MPI program. So it has multiple data flow engines that are able to evaluate different parts of the Swift program at the same time. They're able to store all of the, possibly billions or whatever variables that are in the program. And then it has a distributed load balancer underneath called ADLB that I'll talk about in a minute. So now we're able to go up to about 1 billion tasks per second. And that rate was actually set on Blue Waters a couple of years ago on 500,000 cores of Blue Waters for a synthetic application. So that's kind of how we kind of migrated Swift K, which was a Java-based workflow engine for the grid, to a MPI-based workflow engine for exascale. So the way Swift does that is it basically takes a program like the one shown, which is again a Swift language program, and it explodes it into all of the component tasks. So each little operation there is considered a task with its input and output data dependencies, and then basically we just distribute that workload to the load balancer, and we let it sort it out at runtime. So we kind of the compiler does a lot of optimizations and things that I'll talk about later, but it essentially it's just exploding the program into all of its component primitive operations, and then you end up with a very big data flow. Of course, that data flow graph actually can grow at runtime, so it's not a static DAG. Because of the conditionals and recursive function calls and things like that, the DAG can actually grow at runtime. So it's not completely unrolled at runtime at any given point in time, although it unrolls during runtime. So kind of putting that together, what Swift T really looks like is it's an MPI program that has some control processes that are evaluating the Swift program, and a whole bunch more worker processes that are doing the executing the user code. So again, that's part of that hierarchical programming model I mentioned earlier, where most of the work is done in existing codes, scientific simulations, analysis codes, things like that are typically implemented in other languages. They could be standalone executables, or they could be libraries, or they could be snippets of Python code or R code or whatever else. And we are able to actually bundle these interpreters like Python, R, Julia optionally at configure time, so that basically if you have a snippet of Python code, you can just pass it right through the Swift syntax into a Python interpreter that's running on a compute node, and that allows these tasks to execute very quickly. You don't have to start up Python, you don't have to reload your imports, all that kind of stuff. That's really useful, for example, if you're using machine learning nowadays, for example. I'm doing a lot of machine learning workflows where we're loading Keras and TensorFlow, and they take like a minute to load on these big systems, up to a minute. But with these features, with Swift T, we're able to just load them once, and then every additional task that's sent to those processes, gets all of its programs loaded for free, and all the training sets are already preloaded and all this other stuff. So we're able to really do things efficiently. So we're able to run, many Python tasks per second. We have this unit, the MegaPython. How many MegaPythons can we run on Blue Letters? Well, we've done 14 MegaPythons. So that means starting a new Python interpreter from scratch. Of course, it's in memory, adding 2 plus 2, and then tearing the interpreter down. And again, you don't have to restart the interpreter. You actually keep it alive, and I'll talk about that more later too. Okay, so fundamentally, what is SWIFT built on? Fundamentally, SWIFT is built on MPI. So you have, at the lowest level, it's essentially just sending messages around like you would do with any kind of other MPI program. We use to save a little bit of, software engineering. I guess we have this kind of middleware underneath, I guess you could say, that's called ADLB. That was originally developed by Rusty Lusk and Ralph Butler here at Argonne. And it is a MPI-based load balancer. So it has a put-get interface for putting tasks in. It has a network of masters, so it's scalable. There's no single bottleneck. The masters can share work. And so essentially when you're producing work in Swift by the evaluation of a SWIFT program, all of those tasks, like those Python snippets and whatever else you're generating, command lines, they go into ADLB, and ADLB is able to find a worker for them to run on very quickly. So essentially all we have to do is translate Swift code into an ADLB program, which is what our compiler does. So now I'll talk about a few more applications. We had a nice collaboration with the NAMD team at University of Illinois. They were looking to revamp the way that they were doing replica exchange, which is a biomolecular simulation workflow. And basically what you're doing is you're running a bunch of NAMDs, and every once in a while they're going to stop and exchange data and maybe send some data to VMD for visualization. So the question was, could we improve on the existing collection of static tickle scripts that they had to do this? And basically what they did was they re-architected the way that their replica exchange workflows work, and they also kind of re-architected the way that Swift worked, which is a real neat kind of surprise for us. So basically, a typical Swift program is kind of shown on the left, where you have your workflow program, and then you have the SWIFT runtime, which again is based on MPI and ADLB, like I said, and you call down into often you can call down into actual libraries, so C++ libraries through Swig generated interfaces. And we thought that would work great for NAMD, because NAMD is already based on Swig and Tickle and C++ underneath. But what they ended up doing was they re-architected it so that NAMD would call down into the Swift program and call down into Swift and execute the Swift program. And then the Swift tasks would actually be Tickle snippets that would then call up back into NAMD. So it was a real kind of inversion of control model. And then NAMD would then have these parameters that it could then farm out using its existing mechanism. So this is a really wild re-architecture of how SWIFT works, but it really went to show how reconfigurable Swift was and how flexible it was, and how this mixed language programming model can really help a lot of different kinds of applications. Another interesting application for materials was with EXMATEX, which is one of the co-design centers for DOE. And in this model, we had essentially it's a multi-scale materials model, where at one level you're doing multi-scale modeling, and then if you do not have the information to do the multi-scale, to do the coarse grain modeling, you need to call down into a molecular dynamics simulator. So you're essentially, your workload is dominated by these calls to molecular dynamics codes. So again, that's a great many task workflow for Swift. So basically, we started by looking at CoMD, which is a few thousand lines of essentially sequential C code. So we basically just took that, and to try to scale things up with SWIFT, we recompiled it as a library, so we don't have to fork all the time, and we can just call into it very quickly. And then we took the co-HMM part, which was about 300 lines of C. That's the multi-scale, actually the coarse grain model. okay, and that was about 300 lines of C, and it was calling down calls into CoMD. We basically took CoHMM and rewrote it line by line from C to Swift, which wasn't that hard because, again, Swift looks a lot like C. So we were able to do that. And then just by the fact that we had that, now we were able to call CoMD concurrently because basically we have a Swift program instead of a C program. They were using popen to launch CoMD. We're able to just call CoMD as a library, and then we're able to run it, much more scalably and more importantly, in parallel. So we're able to basically do the same workflow, but it's now it's a parallel workflow and it's calling things in memory. So here's an example with parallel tasks. So in this case, we had DATAFLOW plus DATA-PARALLEL. So we had a user that wanted to run his graphics generating application, which is called OSUFLOW. And we wanted to run many of these. You could do this for a lot of reasons. In this case, the kind of toy justification was to see what the best parameters are for OSUFLOW. What's the best way to run that in terms of processes and things like that. And ultimately, all of these applications are library executions are generating these flow line viz figures. So basically we had, a program that has many parameters, how many processes you give it, how you block the data. And then we had this, essentially this two-dimensional parameter space of, processes and then this block parameter thing. So the question again was, how do we pick the best combination? And we just decided we were going to brute force it here. We're just going to run all of them. So we have all of these parameter combinations. But we needed, in this case, to be able to call into MPI libraries because OSUFLOW is an MPI library. So we built the features in Swift to do that using MPI com create group, which is a dynamic way to create a communicator. And we exposed that through this at par syntax, which you can kind of see here, where that is going to call this MPI draw program on NP workers at a time. So the number of workers is chosen at runtime by this arithmetic here. And then Swift is going to then find NP processes to pool together, call MPI com create group, and launch that library on that dynamically created communicator. And MPI draw itself is actually linked here to an external function in C++, and we denote it as an at par parallel function. And it basically just takes its block parameter and it's the parallelism level, so those are the two input parameters, and the output is just the runtime, so it's a float, in seconds. And again, the point of this was just to see which combination produces the best runtimes. Now we also have a feature in SwiftT that makes it very convenient to call MPI executables as well. So standalone executables can also be called using this feature now. But then basically at runtime, you end up with a jump shot diagram that looks like this, where time is going from left to right, and from top to bottom you have all of the ranks in the run. And I think this is a few hundred ranks, and you can kind of see that Swift has kind of tried to fit all of these tasks in at different sizes and at different times. And then it has filled in the parameter space with all of the the timing data for all of the parameter combinations, and we were able to easily make a little heat map or whatever based on that, and then find the best parameters. So, and this matched up with what the graphics guys kind of already knew, but they had never been able to run every combination before. So this was a nice validation of some of the parameters that they had chosen for their application. Another nice commonly used parallel code is LAMPS, right? And that has a MPI library interface already where you can pass it a communicator and it'll run. That means it's a great fit for SwiftT. In this little workflow, we're just doing a parameter sweep over temperatures, where each temperature is 300 plus I for a range of I's, and we're doing some substitution here, string substitution essentially in the input file for LAMPS, and then running LAMPS on 8 processes here with its arguments. Now the LAMPS API is interesting. It's a C++ function call, or C++ function call, but it takes something that looks like a command line, a list of arguments. So we essentially just have to generate that command line as a string and pass it into LAMPS. And that demo is available on GitHub if you're interested in looking at it in detail. Another just little fun application example, but it was actually based in reality. We had a user that was looking at different kinds of code generation and optimization for numerical libraries, and she wanted to compile the same code a bunch of different ways on a big computer, right? Like on a Cray. So we were asking the question, well, what would it look like if we essentially try to do a big parallel makefile in Swift? How would that look? So we basically wrote a makefile in Swift, and it's able to be deployed on a big machine. I'll go into that in a second. I have a question. On 22, the for each loop is not parallel. So again, in Swift, so the question is, are these for each loops parallel? And the answer is yes, because again, everything in Swift is parallel and eligible to run at the same time, limited only by data dependencies. So, and actually this program does not have a lot of data dependencies, except, for example, this NP here, that's going to be calculated by rounding 2 to the n. We're doing exponentiation so that we can do a nice little parameter sweep. So for each exponent here, we're generating these power of 2s here, because we want power of 2 processor counts. So NP is then consumed here. So there is a data dependency from here to here, but there is no data dependency from one loop iteration to the next. So each loop iteration is eligible to run concurrently. But it does, so typically a Swift programmer will order their statements so that it looks like there's an instruction pointer going down from step to step, like I've done here. But I could have just as easily reordered these statements, and the program would have the same semantics. Okay. Okay, so a little bit more about this makefile example. So to do a makefile, you basically, and if there's any other questions I missed, please just repost them in case I missed it pop up. So we basically just have to, just like in Make, you have to define all of your recipes. So in Swift, we define recipes, but what's nice in Swift is that we have data types, right? So we can define a data type that's a C file or an object file, and then you can get type checking. We also have, you have to pass arguments around in Makefile, your C flags and these other things, but Swift has structured data, so you can actually have an array of strings instead of just a big, one big monolithic string that might be difficult to escape and everything like that. And then basically, so all of these, you make yourself a little library here of your compiler commands, linker, running, and then here's extracting the runtime data from the run. So again, what we're trying to do is compile things a bunch of different ways, because this user had these code generation techniques, and she wanted to run things, compile and run things a bunch of different ways. So this library, you build yourself a little library like this that can do that, and then you write yourself some loops or whatever else. In this case, this is just a toy example, so we're just looping over the GCC -O levels, but you can envision that you could run some shell script or something that's going to generate code and then compile it and run it. And again, this runs in parallel. It'll run on a Cray, and so then you can run a million GCCs or whatever you want to do, and you're not limited to your local machine. Something more reasonable might even be just doing this on a cluster, right? Maybe not on a system like Blue Waters, but maybe on another cluster where you have 8 nodes or whatever, and you want to make them all essentially execute the same build system, or it could be an automatic testing system, nightly testing kind of system. Those kinds of practical tasks could also be done with Swift. They don't, Swift doesn't have to just do scientific workloads. It could also do some of these more practical workloads where you want to distribute work across nodes. Then a few special features for scalability. So I have an example here of expressing a MAPREDUCE-like workflow in Swift where you have a map function here. So the map phase is essentially just, for each loop or for each input parameter, we're going to run some map function. Again, I'm not showing you what the map function is. That would be up to the user to define. And then the reduce phase is, what we're doing here is kind of like a pairwise merge. This isn't the only way you could do it, but this is kind of an easy way to, a compact way to express it on one slide. So we're essentially, we're generating this array that has integer indices, and then we're just going to go through and recursively merge pair. So we're going to merge pair of the merges of the indices shown there. And that allows us to kind of do a recursive function that is going to merge all of those things, all of those data products, D of the data products from the map function. We're just going to merge all of those data products into a big output file that's then called final.data. And the data flow diagram is then shown here on the right. And one thing that's kind of interesting about this implementation versus the typical implementations that are out there is that there's no barrier here, for example, between the map phase and the reduce phase. It's all just based on those individual data dependencies. So as soon as D, 0, and 1 are done, that merge pair will then begin to execute, or at least it will be eligible to execute. So if there's any stragglers or anything like that, you're not going to be blocked at the map phase, like you would be in the, from what I've heard about the existing implementations. We have some features for big data. So we have location syntax in SWIFTIT. So if you have data at a certain location that's maybe on a cluster and you have data at a certain place, maybe it's in temp or maybe it's in a system like memcached, you can send data there. So you can, and we have pretty rich features for doing that with hard and soft location specifications. And we had a student that did a lot of work with that with memcached. And there's other ways you can use those features too. They're very generic features. So you can do kind of data intensive cluster computing. And then we also have features for collective I/O. And these were actually developed for these APS workloads, these experimental science workloads, where we're bringing large quantities of data from an experiment center, like the APS, and then loading it onto a big system like the Blue Gene. So we needed to be able to use MPI/IO to do that. And then so we were able to use Swift to load this data up and then run a workflow over it once it's been loaded into the temp on all of these nodes. So this is a little bit more about task locations. I'll skip over that for now. Another neat feature we have is task priorities. So you can easily annotate a task on a per task basis with a priority. One thing you can do with priorities is if you have some estimate of the runtime of your tasks, you can prevent the long tail effect. So the long tail effect is you have straggler tasks that are running for a long time, and let's say you have a big allocation of 1,000 nodes or whatever. If that one task runs for an extra several minutes, that's burning up your allocation hours. If you know something about that in advance, you can prioritize the long tasks to run first, and then the smaller tasks will fill in the gaps at the end. So in this is actually a real application here. It's only run on 32 processes, but we were able to identify, we had a rough idea of what the task runtimes were, so we just prioritized those tasks to run first. So the load with priorities drops off much more quickly, which means we have a shorter overall make span time. And we pretty much totally eliminated that long tail effect. But again, that's because we had good runtime estimates. Priorities might also be used if you had something with a human in the loop or something where the human is watching the output come in and there's certain information you want to produce first. I mean, that might be another case. There's lots of things you can do with priorities. That's a pretty generic feature. Okay, one kind of big thing we're looking at now is model exploration. So I hinted at this earlier with the cancer example, but what we've done in collaboration with some other computer scientists here at Argonne is build a system called EMEWS, which is a Swift-based kind of a set of conventions and libraries and tools that can be brought together to do model exploration. And what we mean by model exploration is we just kind of mean something kind of generic, where you have a parameter space. A lot of times it means optimization. You're trying to find some kind of interesting regions in this parameter space. But you might also be doing something else like active learning or clustering, or I don't know, there's lots of things that could be done. But there's some of the key features of this are that you're essentially using Swift to distribute work, but you're using some existing library to do a lot of the actual control. So you're delegating control from Swift into some other library that's going to generate these parameters for you. So for example, in this example here, we're using Deep, which is a third-party evolutionary algorithms library in Python. And Deep is then generating all of these parameters. So from one generation to the next, and by generation we mean evolutionary algorithm generation, we are getting the parameters from Deep and then farming those parameters out in a Swift for each loop to this simulator called Repast. So all the workers are running Repast tasks the way they would normally do in Swift. It's load balanced by the Swift load balancer, and then the results come back and they're fed into deep. And we have, some of the features we're using again are the ability to delegate control to this library, Python or R library. And then we also have these queues so that you can actually communicate with this library without waiting for it to exit. So a lot of these libraries have an interface where you provide them a function, right? And then you say, optimize this function. In this case, we're able to, you give them a function that essentially means callback to Swift, and it does that over this queue. This also has to do with the idea that we have stateful interpreters. So Swift is able to call into Python and keep that interpreter alive and call into it over and over and over again. So you can maintain the state inside of a Python interpreter. You can use the location information as shown here to relocate your Python interpreters and actually send work to them. So if you have data cached, say, in a Python interpreter, you can send work to it again and again and benefit from that data cache. So you can have data in a global variable, for example, in a Python interpreter somewhere. You just need to remember its rank and you can send work there. So you can mix this totally freely load balanced kind of programming with something that knows something about locations. I'll just pause here for any questions because this concludes the slides, and then I'm going to switch into the demo. Okay. No more questions yet. Okay. All right. So just here are some links, and I think these slides will probably be distributed or posted after this. So I have a few links here. We have a link to the Swift homepage, a link to the Swift user guide, the Swift sites guide, which tells you how to run it on different machines that are out there, including Blue Waters. A link to the Swift GitHub, which has the active source. All of the source for Swift is on GitHub. Everything is open source and in the publicly visible. We have this tutorial. Okay, so I just have a question. Is there a way to read a JSON file in Swift? No, but we want to have a JSON file interface, and we are looking at doing that. It would be good to have something because a lot of times people have configuration files or other things that they want to look at from Swift or in a workflow and maybe do some task for each entry in the JSON file. Yes, we want to do that. The easiest way to do that right now is, again, by using our Python interface and using the nice features for JSON in Python. And we actually are doing some things like that. So if you get in touch with me, I could easily send you a snippet of code or something like that to show you how that's done. But yes, we do want to do that. So this tutorial is also in Git, and so the scripts I'm about to run are also in Git and this link here. And then we have a mailing list for support. And then I also wanted to send you a pointer to this new project, new NSF project, to essentially bring Swift-like functionality into Python. So it's a pure Python library that lets you do some things that are kind of in the spirit of what I've talked about. And that's a new project that is undergoing a lot of active growth right now. Okay. So again, let me know if this is not visible. So I'm going to log into my Linux machine here and cd into the tutorial directory. So you can see I'm running from the Git clone here. And so I have the 5 examples that I'm going to go through over the next 20 minutes or so. So I have a hello world. I have a loop that's going to expose some parallelism features and things like that. I have an example of BLAS where I'm going to call directly from Swift into BLAS in memory, which is kind of an unusual thing for a workflow system to do, but it just goes to show what kind of things you can do. I have a Python example that's going to show a very simple use of Python from Swift. And then I have a NumPy example where I'm going to show how NumPy can be accessed from Swift also, which is basically the Python thing, but just a little bit richer. So I have this hello example, and it basically just has I can remove these. Those here. So I have hello.swift, and I'm just going to open it up in the editor here. So this is a typical Hello World Swift script. Swift has a nice feature for loading the different libraries that are in Swift. So it has IO libraries, system libraries, things like that. You import them using something that looks kind of like the Python import syntax. And then we have a printf that does everything you would expect printf to do. But in this case, it's just hello world. And so to use that, so I'm just going to put Swift in my path. So I have a SWIFT running. And so I can just simply run it on hello.swift. And so again, Swift looks a lot like a typical programming language. You simply just run it on the workflow script that you want to run, and it essentially runs in place and the output comes to the screen. That's again in the most default and simple use case. Swift is really behind the scenes is running two steps. It is running a compiler and a runtime. So the compiler is called STC. So just to break this down, again, you don't have to do this, but this just shows how the thing works. You can compile the script locally, and that's actually a Java program. So it's kind of portable, but sometimes it's you may not want to run it, for example, on Blue Waters, although you certainly can, and I do. But and then you can run the runtime separately. I'm going to add that to my path too, because I just started a new session here. So now when I ran STC, I then generated this tick file, and that's actually the runtime code. That's essentially the code that's going to run at runtime. And then I can run that with the Swift runtime. And the Swift runtime is, again, a pure MPI program. It runs relatively quickly. I can run it, I can, for example, pass MPI exec arguments like -L into it and get the rank numbers out. I can provide additional ranks, but that doesn't change the Swift semantics here. So this isn't like MPI where if you give it more processes, it's going to do multiple copies of the thing you're doing. It's still executing only one printf because that's all you've asked for. Okay, so it's not like, you might think in an MPI world, you would normally expect to get 8 hello worlds out here, but since this is Swift, it's only going to do one because you only asked for one. If I wanted more, I would need to express a loop or something like that to get the number that I went out. And that's what I'm going to do in my next example. And you don't need to use the separate steps to do this. You can provide those same arguments to SWIFT on the command. Okay. If there are no questions about that, I will move on to the next example. So in this example, I have a small loop. I am going to, actually I don't need this anymore. And what I'm going to do here, so now what I have is a task. So I've just called it task. I don't have to call it task. But I've called this app function task. Again, this maps a Swift signature, which is going to take an int and produce a file. And I want to paste the integer and the file name onto the command line for each execution of this shell script. And I will show you the shell script. It's just simply going to print out what it's doing. It's going to say I'm pretending to compute something. I'm going to pretend I'm computing, so I'm going to sleep for the number of seconds I'm given, which is I. And then I'm going to produce an output file. So argument number 2 is an output file. That's that O. I'm going to put some output into that output file. So where am I going to get all these file names? I want to do it in a loop. So I'm going to do it 9 times here for I from 1 to 9. And I'm going to generate file names here inside the body of this loop. I have a couple of questions about the technicalities of PBS. I actually wanted to run a PBS job, so I'll show that at the end. I'll show you what I've got running there about PBS and setting up these things. And one second. So I'm going to CD to this second example. I'll just run it to show you what it's trying to do. So it's looping, and again, each task is going to run for several seconds. So it ran task 1 first, and now it's on task 9. That's going to run for 9 seconds. And then eventually we're going to get, okay, now it's running the 8-second task. Okay, so that's running too slow, right? So I want to get this done more quickly, so I'll cancel it. I'll just provide it, I don't know, 20 processes, right? Which is too many, but that's fine. And then I'll ask it for the rank numbers that it ran on with -L, and let's run it again. So now it's running all those tasks at the same time on different ranks. And now you can see them complete. So, the 1 second task completed first, then the 2 second task, and so on all the way down to task 9. So that whole thing ran in about 9 seconds. And it generated these output file names with this syntax. So we have the Python-like string format operator, %, and we're just going to populate this string format specifier here, %I, with the value of I, which is an integer here, stick it in here, so then this file variable, f, is mapped to the real files that are generated with this string operation. And those, because they're assigned here, those file names get stuck in O here, which is the output of task, and then they're pasted onto the command line here. So we're able to generate all these files, and then they're in my directory here, so I can cat them or whatever I want to do. Okay, let's pause here for questions. So the step-by-step setup for non-admin on my local Slurm cluster. So I've gotten kind of 2 questions on this. One I think was about PBS and the other is about Slurm. So I will now pull up the sites guide just to kind of show how this document is structured. So we have the Swift main entry point webpage, which is also, I gave it to you in the PowerPoint, which will be available later. We have the Swift guide, which tells you more about the language. And then we have the sites guide, which tells you how to actually get it running on your systems, which I think is what the questions are coming in about. And this tells you a little bit about, what Turbine is really doing as an MPI program, how to submit it with all the different variables it accepts. And then I have a big laundry list of machines that we have installed Swift on. And we can definitely add to this list at request. But just as an example, I'll go to Blue Waters. So I have, to run it on Blue Waters, you simply just need to add these path locations to your bash scripts or whatever you want at startup time, and then you can run on the login nodes. The compute nodes, they're different paths for the login and the compute nodes because they are, again, it's an MPI program, so we're using different MPI libraries. So when we run on the login nodes, obviously do not abuse the login nodes, but for quick tests, I think it's okay to run it. And this uses mpitch because it's just running on the login node. It uses a custom mpitch. But on the compute nodes, obviously we're using Cray MPI, so those are different Swift installations. And here's an example of how to submit on Blue Waters. You basically just provide a few environment variables, such as the queue you want to submit to. There's a magic variable here that is for a specific, to turn on a specific feature for Blue Waters. You can provide your project, things like that. And then you simply say mcray, which will then generate and submit a Cray formatted submit script. And I can show an example of that in a minute. And then they'll submit it, it'll create an output directory, and it'll run this workflow in that directory. And it'll give you a job ID, so then you'll have your job ID, because it's running one MPI job, right? And then I have the build procedure here for these different systems. And so each section has, the quick start guide for the public installations, and it also has the build notes. So for example, on Cray, you need to provide this, all the Cray flags and things like that to get something built. But typically I have done that for you on most of these known systems, and I'm willing to install it on other systems as well. Okay, going back to the tutorial. And then there's examples in there for the person that asked the question about Slurm. There are some Slurm examples in there if you take a look. Okay, so now I'm moving on to the BLAS example. So this is where I said I was going to show this kind of unique feature in Swift for using calling directly into libraries. So in this workflow, which probably doesn't look very much like what you'd normally think of as a workflow, but this is just a kind of a toy example to show what kind of things you can do. Again, normally we would call into some component like a whole simulator or something like that, not into just BLAS itself. But this is just kind of a stunt to show that we can call into Fortran compiled libraries, right? So in this case, we're just going to build up some arrays in Swift of floats of size 3. We're going to populate them with this int to float things. We're going to iterate over I, which is an integer, and then stick those values into A and B. And then what we're going to do is do a D dot, which is, a dot product, using BLAS on A and B, and their size is n. So this looks just like the BLAS call for D dot, and then we're going to just simply print out the result here. And the way we did that is, well, there's a matrix library in Swift that gives you some of these features. And then we also have a BLAS library here that we have built with this BLAS example. So if I look here, what I have the .swift, which is the workflow that I'm actually running. That's this script. But then I have this header called blas.swift. And this has all of my mappings from Swift to, in this case, we're calling into Tickle because we used SWIG. So remember how I said that, NAMD is for an example of a system that uses a lot of Tickle scripting over C++. So they use SWIG to generate Tickle interfaces, and then they are able to do rapid code development with Tickle. Similarly, we did something like that. You can do that with Swift. You can do that with Swift with Tickle or Python or R, things like that. In this case, we're using Tickle, and we're mapping this is kind of like an app function like I showed before. We're mapping a Swift signature, which has types and everything like that, into this Tickle command line here. And this Tickle function is actually mapped to the BLAS library. So again, this is something you can do with SWIG, where you can generate yourself a Tickle library for a native code library, and then you can very easily call that concurrently from Swift. So that is just, going to take X and Y, which are these blobs. Remember, like I said, blobs are binary strings. We are generating them in Swift here with floats to blobs. So we're taking a float array and converting it into a blob, which is, like a C byte array or something like that. So it's, it's just a binary string. And then we're passing that in here, and so then this is something this is essentially the BLAS interface for D dot, where it takes the number of, the size of the arrays, and then the actual pointers to the arrays, and then it produces this float as a result, which is returned here as float Z, which is returned here as float Z, and then is going to be reported with printf here. And this, one other little minor bit of Swift syntax. So like I said before, you typically express Swift programs in order, even though you don't have to because they work in DataFlow order. But if there are side effects or other things like that, and you want to impose some order, even though there's no real data dependency, you can use this arrow operator, which we call the chain operator, which will then chain these statements so that you can insist that they operate in order. And that's useful for things like printf, where you want to print things and have them come out in the order that you did that you specify. So you can print an error message or whatever you want to do. That makes sense. So you can use this to force order. So I'm going to print out A, I'm going to print out B, and I'm going to do the BLAS thing, and then I'm going to print out Z. Now Z has a data dependency from Z to Z here, so I don't need a chain there. So again, to run that, what I need to do is I need to, now I have this build script to build the interface to BLAS, and that builds this, essentially a Tickle package. So I need to just point Swift to that. So I need to set the Swift path variable so Swift knows where to look for libraries. And then now I can run .swift. And you can see, just like the program specifies, it prints out the values of A, it prints out the vector B, and then it reports this line that shows the dot products of the two. Any questions about that?
Yes, there are a number of questions. Does he hear us? Okay, so the first question is, does turbine-N8 spawn a maximum of 8 workers?
So turbine-N specifies the number of MPI processes. And there are 2 kinds of processes in Swift, servers and workers, in accordance with that ADLB diagram I showed previously. By default, you get 1 server. So that would mean that you have 7 workers. And you can easily change the number of servers with an environment variable that's in the manual. But the point is that we say -n it should be like the MPI exec minus n or the other minus n's that you're used to. So that is the number of processes. And then some of them are going to be servers, by default 1. So and if I do not provide minus n like I did here, I have 1 server and 1 worker. So this is actually running 2 processes total.
Okay, thank you.
So the ranks, you'll see that rank 0 is the worker, and rank 1 doesn't say anything because it is the server.
So the next question is, if there is a loop without any data dependencies between iterations, then the iterations are run concurrently. Are all iterations run concurrently? Is there a limit on how many are run concurrently?
Okay, so how many concurrent, what is the, how concurrency semantics for loop? So for example, here's a for loop. All of these assignments are eligible to run concurrently, but it is limited by the number of workers. So now actually this is not a real task. This is probably just, this is done by generated code. But if you had a real task, like in the loop example, we have, you know, these tasks, and well, so I ran this with 20 processes, right? But let's say if I only give it, now I've asked for 9 tasks here. If I only give it, say, 4 processes, then I have 3 workers. And then you'll see that 3 of them run at a time. Well, it's not that obvious because the run times are different for each. But yeah, you can see I'm running 987 and then 654, and then I'll probably run 321 here at the end. Or I guess 1, 2, 3 ran first. So they did kind of run in groups. So, and then you can see which ranks they ran on: 0, 1, 2, 1, 2, 0, 1, 2, 0. So, and then rank 4 was the, or rank 3 was the server.
Okay, so the next question is, does a master in SWIFT-T run loop iterations, which in turn could spawn workers?
We do not spawn workers, we spawn tasks, because the size of the number of workers is specified when you launch MPI exec or AP run or whatever. So we cannot spawn additional workers, we just reuse and load balance among the workers that we have.
Thank you. The next question is, does SWIFT-T have malloc?
SWIFT-T has a blob library that allows you to work with blobs. So remember, in SWIFT-T, all of the data is stored by Swift and passed around, right, from task to task. Like in the blob example, in this dot example, I'm generating these arrays which are going to be turned into blobs, and then when d dot runs, that data has to be sent to the worker that is running the blobs call. So you malloc, obviously means you're mallocing something in a certain location. Swift variables don't really have a location like that. They're stored in a DHT, and they are sent to wherever they need to be consumed, and they are reference counted and garbage collected at runtime. So malloc doesn't really make sense in the Swift world. What you would do is, call into a task or call into native code and malloc there, using your typical tools. Normally, you would want to free any data like that at the end of your task, unless you really know what you're doing and you're going to send another task there later on and maybe reuse some of that data, which people do. But in general, to allocate blobs and things like that, you use our blob library, like what's shown here, where we are converting an array of floats to blobs, for example, to an array of floats to one blob. And,
okay, thank you. The next question is, can Swift be configured to use BLAS from Intel MKL?
Yes, sure. Yes, you can use any native code. Basically, all you need to do for example, generate this example is, we would normally use Swig to generate this BLAS wrap .c thing and then run it. BLAS, this package that I generated with this build script that's provided and shown in Git, this build script shows how this is done. It's a few lines of GCC. This library is linked to, you can see OpenBLAS here, but that could be anything. I mean, it could be your own code, it could be any code. You just need to be able to link against it.
Okay, thank you. Next question is, we have a lot of questions today. So how does SWIFTIT pass variables between functions? By reference?
They are passed by, yeah, you can say by reference is probably the best way to think about it. SWIFTIT variables are stored on the servers, and that's another important reason we support multiple servers, is that you may have so many variables that, and so many blobs and other kinds of things, that you need multiple servers to store all those variables. If you're going to run billions of tasks, you might have, of course, billions of variables. So they're stored on the servers, and then when a task executes, it can retrieve the data it needs from the servers, which it basically uses a DHT-like lookup mechanism to find its data and run.
All right, and one more question. If there is no malloc, how can I do float array of n, of size n, in SWIFTIT for any large n? So how can you allocate that?
So for example, in this case, I'll flip my editor here again. I'm just going to get this quick because this is a pretty, we might want to take this conversation offline, but basically, for example, in this case, we're going to generate an array, right? And in Swift, you don't have to tell it how big the array is going to be. It can figure that out at runtime. And we are simply sticking these floats into the array, okay, n times. And then inside of this function, we are converting that array into an array of, or into a blob, into a single blob. Okay, so there's no, the normal things you have to worry about with malloc are, the size and, the lifetime of the object. Swift basically takes care of that for you because, you're going to generate a blob normally using some Swift functionality, either converting an array into a blob or converting a string into a blob or something like that. So that blob is going to be allocated for you, and the malloc's going to happen for you, and then again, it's going to be deallocated for you when the reference count hits 0. So, so Swift abstracts away some of the, the mechanics of using malloc. But again, I also kind of want to stress, this is a stunt application here. Normally, a user would not be using BLAS directly from Swift. Normally, you would call into your scientific code, your simulator, your analysis code, things like that. You have, that is going to be a much coarser level than this example.
All right, thank you very much. I'd like to thank you, Justin, and also all participants who were very active in the Slack channel and were asking questions. Please join me in thanking Justin for a very useful webinar today. I hope that it will stimulate you to investigate what you can do with SWIFTIT or how can SWIFTIT apply improve your code or your application. The next webinars, we have a special, unusual webinar, actually the first one in a series, in a new series of software engineering. It's called Software Engineer. The webinar track is called Software Engineering Track. And the webinar next week will be presented by Jeff Carver. Please join this webinar. It will be interesting. And we also would like to announce yet another webinar track. It's called Workforce Development and Inclusion. The first webinar will be given by Tony Collis, and it is titled Opportunities and Challenges Diversifying Your Workforce. It is scheduled to run on October 18th, so please join us in October. There will be no webinars before that. And today, or probably honestly later this week, you will receive a summary of this webinar with a short 5-question survey. Please, if you have any comments or suggestions, please let us know using this survey. And with that, have a good week, everyone.